Looks to me that whoever wrote question 3 was trying to be deliberately awkward, because the whole point about questions to do with moments is that you need to know exactly where the forces are acting. And here they've sort of really gone out of the way to deliberately sort of say that it's supported over a length of a metre at each end. So where exactly does the force act? They've clearly decided, as they solve the question, where exactly the force acts. Unfortunately, they've got it wrong, because the answer they've got is impossible. I've tried to get their answer by looking at the back of the book and trying to decide where to put the force, and I decide that in order to get the answer they've got, it must be pivoting somewhere off the end of the beam, which is complete nonsense. So, forget trying to get the answer in the book. Try and make sense of this question. To do moments questions we need pivots. Pivots have got to be in exact places. Now if I was answering this question, you can't say the pivot is spread over that metre at the end. That doesn't make sense, it's got to be in an exact place. The way that I would answer the question would think, what would that bridge tend to do? With a lorry on it, or even without the lorry, if anything, it would tend to sag a little bit and sort of bend downwards like that. In which case, if you think what would actually happen, the points where it would be supported would be right on the edge there and right on the edge there. So if I was going to be answering that question, I would draw a picture where the support forces would be 1 metre from each end. Once I'd done that, simple matter of putting the numbers in, applying the principle of moments. It's then a beam supported at 2 points, so we know that the 2 points where it's supported, we can treat those as pivots. Imagine that one of them, it would tend to turn clockwise around it, except it doesn't turn clockwise because the other one's holding it up. And then think about the other pivot, the beam would tend to turn anti-clockwise around it, except it doesn't because it's been held up at that side. So it ends up being like the previous examples that we've done. As I said, the answer in the back of the book was wrong, and whoever wrote the question was trying to be deliberately awkward and made a mess of it by getting it wrong themselves. Question 4 is about a plank that's supported on bricks. And we've got to remember that if it's supported on bricks, it means that the bricks are providing an upwards force. So we don't need to draw bricks, we just need to draw upwards forces. So it says 1 brick is at the end of the plank, the other brick is 1 metre from the other end. So I say I don't draw the bricks, I just draw forces. There's a brick supporting one end, so I draw an upward force at one end. And the other force is 1 metre from the other end, the other brick, so the other upward force. So upward force provided by the other brick. And it says the plank's got a weight of 150 newtons, and the plank's uniform, so the weight acts in the middle. So now I've got the 3 forces. I've got the downward weight of the plank, I've got the upward force provided by one of the bricks, I've got the upward force provided by the other bricks, and of course, if this upward force wasn't there, the plank would pivot about the left hand side and drop down. But it doesn't pivot and drop down because that force is there holding it up. So we could treat this place as a pivot if we want. Equally, we could treat this as the pivot. If that was the pivot and this force wasn't there, the plank would pivot down, would turn anti-clockwise. But it doesn't pivot down because it's held up by this force that's provided by the brick. So we can treat either of those 2 places as a pivot if we want. It doesn't turn because it's in equilibrium. So it makes sense to give places names, so I can call that point A, call that point B, give the forces names. Obvious name for a force that's at A would be FA. Obvious name for a force that's at B would be FB. I could call them X or Y and P and Q and anything I want, but it makes sense to have organised names. So now that I've got these forces, I know it's in equilibrium, I can apply the principle of moments. So I choose a point as a pivot. So for instance, if I choose to start by having point A as the pivot, then when I apply principle of moments, my clockwise moment, and of course for exam questions we always write total clockwise moment equals total anti-clockwise moment, because you never know, there might be a mark for it. So if I use that as the pivot, the clockwise moment is provided by this force, and I know the distance. The anti-clockwise moment is provided by that force, I know the distance. Put the moments equal to each other, I can calculate FB. And then when I've done that, if I want to calculate FA, I've got a choice of methods. I can either say, well, let's treat this as the pivot and do the whole thing again. Clockwise moment will be provided by that force multiplied by the relevant distance, anti-clockwise moment as far as this thing's concerned. What's trying to make it turn that way? It's this force times that distance. So that's one way of doing it. Or the other way, of course, you know the downward force. Once you've found one of the upward forces, you can easily find the other just by thinking about the total upward force must balance the total downward force. Right, in part B, a child stands on the free end of the plank, so that's here, and it just causes the other end to lift off its support. So a child, I'm trying to find the weight of the child, so call that W. Now it says the child standing there just causes the plank to lift off this support at this end. So the plank stops touching this brick. And if the plank stops touching this brick stops putting a force on the plank. So FA would become 0. Obviously if you're doing this in an exam, you don't start rubbing things out. You do a new diagram. I'm going to cheat. I'm just going to rub that off. I'm just going to rub that out. So now we don't have a force at A. What do we have? We have a system that's in equilibrium, because it doesn't say the whole plank tips up, it says it just loses contact. Just causes it to lift. So it's in equilibrium, it's balanced. If the child was any heavier, the whole thing would turn. But it's just on that point of being balanced. So now it's obvious where the pivot is. Pivoting about B. There's no longer any support force at A, so it's in equilibrium. You can work out what the value of W would have to be.